This is the summer 2020 P3 paper, and it is version 1, so paper 3 version 1. The first question is an inequalities question which involves logs. We always need to be careful with those because you need to remember that the log of a number less than 1 is negative, and if we end up having to multiply or divide by that, then we have to change the direction of the sign. I'm not sure if that's something we'll need to do here. We are going to need to take logs to begin with to maybe try and split some of these terms up. So I'm going to begin by taking logs of both sides. Okay, and we have two things multiplied together within the log here, which means we can split them up as ln2 plus ln3 to the power of 1 minus 2x is less than ln5 to the power of x. Now we can use our power law to bring these powers down. And we can bring this power down as well, x ln5. We're going to need to isolate the x to get x by itself. I'm going to do this by expanding the term on the left hand side here. So we get ln3 minus 2x ln3 is less than x ln5. Let's add this to get it onto the right hand side. So we get ln2 plus ln3 is less than x ln5 plus 2x ln3, and then we're going to factorise to get x by itself. Left hand side is still the same, ln2 plus ln3 is less than x ln5 plus 2 ln3, and then we are going to divide by that. I'm also going to write the x on the left hand side, careful, x is now greater than ln2 plus ln3 divided by ln5 plus 2 ln3. Let's just check what form they want the answer in a simplified exact form. Okay, so let's see what we can do to simplify this. We have two logarithms added together, which means we can multiply these and combine them into a single logarithm. So 2 times 3 is 6. Here, there's nothing we can do with this one yet until we bring this power up using the power law. So I'm going to bring this one up to make it, instead of 2 ln3, ln3 squared. So it will say ln5 plus ln3 squared. 3 squared is 9, so we get x is greater than ln6 over ln5 plus ln9, and then we are going to use exactly the same rule as in the numerator by multiplying these two. 5 times 9 is 45, so we get ln45. There we go, ln6 over ln45. Question 2 asks us to expand 2 minus 3x to the power of minus 2 in ascending powers of x. So it's a binomial expansion question. You can reach for your formula book if you want. To be able to use the form of the binomial expansion that we need, the second version, we need to make this first number 1. So we're going to do that by factorising out a 2. So I'm going to use square brackets to begin with, take a 2 outside the brackets, and inside the brackets, for this to still be the same thing, we would have to have 1 minus 3x over 2. And that whole thing is all to the power of negative 2. Okay? That means that this 2 is now to the power of negative 2 times 1 minus 3x over 2 to the power of negative 2. 2 to the power of negative 2 is 1 over 2 squared, which is 1 over 4. So we're going to do our expansion, and then we're going to have to divide our expansion by 4. So here we go. Grab your formula books if you want to. So it's 1 plus nx So minus 2 times negative 3x over 2 plus n times n minus 1 divided by 2 factorial times minus 3x over 2 squared. And it only asks us to go up to the term including x squared. So I'm going to stop there. Let's leave our quarter outside for the time being. And we have 1. Negative times a negative is a positive. 2 divided by 2 is 1, so we're just going to get 3x here. Here we're going to have negative times a negative, and then we have a negative squared, so again it's positive. 2 times 3 is 6, divided by 2 is 3, we'll take an extra step here, times 9x squared over 4, squaring each of those terms. So we get 1/4 times 1 plus 3x plus 27x squared over 4. And then we're going to multiply all of those by 1/4. So we get 1/4 plus 3x over 4 plus 27x squared over 16. Our formula for the binomial expansion is normally valid for the absolute value of x being less than 1. In our case though, it's not just x, instead it is 3x over 2 that we have used. Sorry, negative 3x over 2. But the absolute value of negative 3x over 2 is exactly the same. So I can just as easily write modulus 3x over 2 is less than 1 instead. Okay. Let's multiply by 2. So the modulus of 3x is less than 2, and divide by 3, and we get modulus of x is less than 2/3. That would be an acceptable answer. It would be just as good to put x needs to be less than 2/3 or greater than negative 2/3. Either one of those two things is absolutely fine. Question 3 wants us to express this equation as a quadratic equation in tan theta and then solve it. You'll notice straight away that it's in degrees, so make sure your calculator's in the right mode. It's also worth noting that this is 6 marks, so we don't expect it to be very straightforward. We have this tan theta plus 60, so let's get our formula book and grab the relevant addition formula. There it is, tan A plus B, and let's just write it down at the top of our page. Tan A plus or minus B is tan A plus or minus tan B divided by 1 minus plus tan A tan B. Let's now apply that to both of those additions. So on the left hand side we're going to get tan theta plus tan 60 divided by 1 minus tan theta tan 60 is equal to 2 plus, and it's a minus this time, so we're going to be reading along the bottom line, and tan 60 minus tan theta divided by 1 plus tan 60 tan theta. You can evaluate tan 60 on your calculator. It's root 3. So let's replace any tan 60s with square root of 3. So tan theta plus root 3 over 1 minus root 3 tan theta is equal to 2 plus root 3 minus tan theta divided by 1 plus root 3 tan theta. Let's try and clear these fractions by multiplying first by 1 minus root 3 tan theta, and then afterwards we'll multiply by 1 plus root 3 tan theta. Let's multiply by this one first, and we get tan theta plus root 3 is equal to 2 times 1 minus root 3 tan theta plus root 3 minus tan theta times 1 minus root 3 tan theta divided by 1 plus root 3 tan theta. Now let's multiply by 1 plus root 3 tan theta. This is going to get quite long this time. Here we go. Tan theta plus root 3 times 1 plus root 3 tan theta is equal to 2 times 1 minus root 3 tan theta, 1 plus root 3 tan theta, and finally root 3 minus tan theta times 1 minus root 3 tan theta. Right, let's expand each of these. We'll do first outside, inside last. So here we're going to get tan theta on the outside plus root 3 tan squared theta, the inside plus root 3, and the last terms plus 3 tan theta. Here we're going to get the difference of two squares, because minus root 3 tan theta plus root 3 tan theta give us nothing. So the only terms we're going to be left with are 1 minus 3 tan squared theta. Here we'll do first outside, inside last again. We get root 3 minus 3 tan theta minus tan theta plus root 3 tan squared theta. Now I'm going to simplify anything I can simplify and also subtract anything from both sides that I can subtract before going any further. So I can see straight away that on both sides I have root 3 tan squared theta. So I'm going to subtract that from both sides. I'm also going to subtract root 3 from both sides. Okay. As our next step now, we will simplify anything on the left hand side and the right hand side and also expand these brackets. So we have tan theta plus 3 tan theta. That's 4 tan theta. Expand these brackets, 2 minus 6 tan squared theta, and minus 3 tan theta minus tan theta is minus 4 tan theta. This is actually looking quite nice now. Let's get everything to the left hand side to keep this tan squared theta positive. So we'll add 6 tan squared theta to both sides. So we get 6 tan squared theta. I'm going to add 4 tan theta, so I get plus 8 tan theta, and I'm going to subtract 2. So I get 6 tan squared theta plus 8 tan theta minus 2 is equal to 0. You should notice that actually this is all divisible by 2, so it's going to make our lives a little bit easier to divide all of that by 2 and get 3 tan squared theta plus 4 tan theta minus 1 is equal to 0. Let's say something like let x equal tan theta, and rewrite our equation as 3x squared plus 4x minus 1. Let's see if it factorises. It's going to have to be a combination of plus 1 and minus 1. I don't think it is going to, so instead let's use our calculator to solve. So 3x squared plus 4x minus 1, and we have two possible solutions. have x is equal to minus 2 plus root 7 over 3. Beg your pardon. Plus root 7 over 3, or x is equal to minus 2 minus root 7 over 3. So we have either tan theta is equal to this, or tan theta is equal to this. I would expect that one of these, let's have a look actually. So inverse tan of minus 2 plus root 7 divided by 3. So our principal value for this one is 12.1. It's in degrees, so we're going to leave it to one decimal place. And for this one, 57.1. So we're going to need two cast diagrams. So for this one, here is our angle 12.1. All are positive in this quadrant, so the other quadrant we want is this quadrant here. To get to this point, we're going to do 180 add 12.1, so that is 192.1 degrees. Is that within? That's outside the domain that we want, so we're not going to take that value. For this one, it looks like I beg your pardon, it looks like I wrote 57.1, it should have been minus 57.1 there. So that on our cast diagram, at the moment that's outside the values that we want. Minus 57.1 is down here. So the other place we want it is up here, 57.1. To find this value, we're going to do 180 subtract 57.1 to give us the value 122.9. Negative 57.1 is outside the range we want, so our valid values of theta are 12.1 degrees and 122.9 degrees. There we go. Question 4 wants us to find the stationary point, the x-coordinate of this stationary point. It's worth noting straight away that this is in radians and the previous question was in degrees. So again, let's change our calculator straight into radians so we don't make a mistake later on. To find a stationary point, we're going to have to differentiate and set it equal to 0. So we're going to find dy by dx. To do that, we're going to need to use the product rule, okay, because we have a product here. So u is equal to e to the 2x, and v is equal to sine x plus 3 cos x. So our du by dx is 2e to the 2x, and our dv by dx is equal to cos x minus 3 sine x. And our product rule says dy by dx is equal to u dv by dx plus v du by dx. So that's e to the 2x times cos x minus 3 sine x plus v du by dx 2e to the 2x times sine x plus 3 cos x. Okay, let's simplify this a little bit. It's probably easier to simplify by maybe expanding first. So let's do e to the 2x cos x minus 3e to the 2x sin x plus 2e to the 2x sin x plus 6e to the 2x cos x. Collect our like terms. So we end up with 7e to the 2x cos x and minus 1e to the 2x sin x, and then let's refactorise e to the 2x 7 cos x minus sin x. We're not asked to put it in its simplest form, but it's going to make life a little bit easier because we would have to do it sooner or later anyway. Because it's a stationary point, we're going to set this equal to 0. It's a stationary point, so dy by dx equals 0. So e to the 2x times 7 cos x minus sin x equals 0. This cannot be equal to 0. It approaches the x-axis, but it cannot be equal to 0. So this is the thing that we're going to set equal to 0, 7 cos x minus sin x. So we get sin x is equal to 7 cos x. Let's divide by cos. So we get sin x divided by cos x is equal to 7. Sin x over cos x is tan x. So we get tan x equals 7. And then we'll do inverse tan of 7. Again, make sure your calculator is in radians this time. And we get x is equal to 1.43. Radians should be 3 significant figures. So 1.43 radians. Let's just double check the question. It does say 2 decimal places. But that is also 2 decimal places, so we're fine. So x is 1.43. In part B of this question, to determine whether the stationary point is a maximum or a minimum, you might be tempted to differentiate again and substitute this value in, which would be absolutely fine, but it's only worth 2 marks, which makes me think that it wants us to do it an easier way. So instead, what we'll do is let's find out what's happening just on the left-hand side of this point and on the right-hand side of this point. So let's try when x is equal to, say, 1.42, and we'll substitute it into dy by dx and see what it tells us. So when x is equal to 1.42, I'm going to substitute that into e to the 2x times 7 cos x minus sin x, again ensuring that your calculator's in radians. So let's have a go at that. E to the power of 2 times 1.42 brackets 7 cos 1.42 minus sine 1.42, and I get 1.077. I get this positive value, so that's telling me that the graph at that point is going upwards, something like that. Now let's try x equals 1.44, something just to the right of this point. And let's again substitute that into the same thing. I can just go back and delete the 2's and replace them with 4's. and I get a negative value, negative 1.398, etc., which means the graph's going like that. What that's telling me is, if on the left-hand side it's positive, it's going up, then we have a stationary point, and then the graph is going down. Well, what's that looking like? It's looking like a maximum point. So we can deduce that therefore the stationary point is a maximum point. Any time when a question like this is just worth 2 marks, this is often the easiest way to answer it, rather than to differentiate again, especially when differentiating again is going to require using the product rule again. Question 5 is a question on algebraic long division. So let's set it up. We're going to write x squared. Remember, we need to write 0x here, plus 3, into 2x cubed minus x squared plus 6x plus 3. So x squared into 2x cubed goes 2x times, and then we're going to do 2x times by each of these. So 2x cubed plus 0x squared plus 6x, and subtract that, and we get nothing here. Here we get minus x squared, subtract 0x squared, so minus x squared. 6x take away 6x is nothing, so plus 0x, and we'll bring this 3 down, plus 3. Now we're going to do x squareds into minus x squareds, which is minus 1, and then we'll do minus 1 times by all of this, and we get minus x squared minus 0x minus 3. So we get nothing here, nothing here. Here we get plus 3 minus minus 3, so we get 6. So this is our remainder. So our quotient is 2x minus 1, and our remainder is 6. We could write this as 2x minus 1 plus 6 over x squared plus 3. Our quotient and our remainder. Part B asks us to integrate what we had in Part A. It's worth just double checking that the two things are exactly the same. I have checked and they are, but sometimes they do things like multiply the whole thing by 2, so it's worth checking. So we're now going to integrate 2x minus 1 plus 6 over x squared plus 3. So here we go. 2x minus 1 plus 6 over x squared plus 3 dx. Now the first part is simple. Given this is 5 marks, that's telling us that the next part probably isn't. It's not something we can, the bottom isn't something we can factorise, so we can't split it into partial fractions or anything like that. It's actually part of the syllabus, which is fairly new, and what they're wanting us to do here is to actually use this formula. It's our arctan formula. Okay, so we'll come back to that in a moment. Let's first of all maybe split it into 2 parts. The easy part, 2x minus 1, and the difficult part, 6 over x squared plus 3 dx. And now what we're going to do is we're going to try and make this look as much like the formula in the book as possible. So in the book it has 1 on the top, so let's also make it say a 1 on the top by bringing this 6 outside. So 6 times 1 over x squared plus 3 dx. Now we've got it just about in that form. It's worth noting that a squared is equal to 3, so if it makes it easier for you to think about it, we could write this as square root of 3 all squared. Okay, now let's integrate. So we have The integral of 2x is just x squared. The integral of minus 1 is minus x between 1 and 3. And then we have 6 times, now the integral of 1 over x squared plus root 3 all squared is 1 over root 3 arctan x over root 3. Okay, let's substitute our limits in now. So here we have 3 squared, which is 9, subtract 3, minus 1, subtract 1, and then we have plus 6 times 1 over root 3 arctan of 3 over root 3 minus 1 over root 3 arctan of 1 over root 3. 9 take away 3 is 6, 1 take away 1 is 0, so here we're just going to get 6, and then we have 6 times 1 over root 3 arctan of 3 over root 3, which I believe is 1 over root 3 times pi by 3, minus 1 over root 3 times pi by 6. Let's just go ahead and simplify this a little bit now. So 6 plus 6 times, here this simplifies to pi over root 3 times by 6. So 6 divided by 6 is just 1, so we are just going to be left with pi over root 3, I believe. I think that's our answer. Let's check what form they wanted it in. They wanted the exact value. So I believe that's okay. Perhaps we could rationalise the denominator, but I think either way is fine. Root 3 pi over 3. So maybe one of those two things. Question 6 looks like it's expecting us to draw on our knowledge of P1, so hopefully we've remembered that. It shows a circle with centre O and radius R. The tangents to the circle at points A and B meet at T, and this is 2x radians. The shaded region... Okay, so the area of the shaded region is equal to the area of the circle. So we're going to find the area of the shaded region. To do that, we're going to find the area of this quadrilateral and subtract the area of the sector. The easiest way to find the area of the quadrilateral, and often in these cases, is to make this into two right-angled triangles. This will be the height. We need to find an expression for the base, TA here. Okay. This angle here is going to be x, and if we use tan x is equal to opposite over adjacent, so TA divided by r. So this side TA is equal to r tan x, and the area of this triangle TAO is equal to base times height divided by 2. So r tan x times by r divided by 2, or a half times r tan x. We can do that because those two sides are at a right angle to one another. So we have a half r squared tan x. This quadrilateral is made up of two of these triangles, so the area of TAOB is 2 times that, so just r squared tan x. For the shaded area, we're going to have to subtract this sector here. The area of a sector, it's in your formula book, but hopefully you remember it is a half r squared theta, so a half r squared, and in this case our theta is 2x. We have a half times 2, so that's just 1. So the sector is just r squared x. So the shaded area is equal to r squared tan x subtract r squared x. We're told that that shaded area is equal to the area of the circle. The area of a circle is just pi r squared. So we have pi r squared is equal to r squared tan x minus r squared x. Let's now divide everything by r squared. And we end up with pi equals tan x minus x. We're close. We're going to add x to both sides, and we get tan x is equal to pi plus x QED. There we go. In part B of this question, we're asked to show that this equation has a root and that it lies between 1 and 1.4. As is often the case in these kinds of questions, your best approach is to set it equal to 0. So let's bring everything onto the left hand side by subtracting pi and subtracting x. Okay, and then all we need to do to show that there is a root between these points is to substitute in 1, substitute in 1.4, and to show that there is a change in sign. Okay, to show that it goes through 0 between these 2 points. So let's try x is equal to 1 to begin with. So tan 1 minus pi minus 1. Let's see what that gives us. Make sure your calculator is in radians. I get negative 2.58, etc. Now we'll try 1.4. So tan 1.4 minus pi minus 1.4. And when we do that, we get 1.256, etc. Okay, so there's a change in sign between these. So the change in sign indicates a root between 1 and 1.4. In part C, I need to determine the root correct to 2 decimal places. I need to choose a value for my starting point. I guess we could choose 1 or 1.4 or anything between that. I'm going to start with 1 as long as it converges. So I'm going to start with x0 is equal to 1 and x1 is equal to tan of pi plus 1. Okay, when I do that, that gives me 1.3339 to 4 decimal places as requested. Now what I'm going to do here for my x2 on my calculator, I'm going to write answer. So I'm going to delete that 1 and replace it with answer, and that should automatically calculate my next root. And I get 1.3510. Now all I need to do is press equals, and that's automatically going to substitute in my last value, and I get 1.3518. And it looks to me like I've already got 2 that round to the same thing, to 2 decimal places. So x2 and x3 both round to 1.35 to 2 decimal places. So there we go. So x equals 1.35 to 2 dp. Question 7 is a differentiation question. We need to show that the derivative is negative for all values of x between minus pi by 2 and 3 pi by 2. So let's start by differentiating. We're going to use the quotient rule with u equals cos x and v equals 1 plus sin x. So du by dx is minus sin x, and dv by dx is equal to cos x, and our quotient rule says dy by dx is equal to v du by dx. So 1 plus sin x times negative sin x minus u dv by dx cos squared x, all divided by v squared, 1 plus sin x all squared. So let's expand this now. We get minus sin x minus sin squared x minus cos squared x over, let's leave this factorised for the time being, 1 plus sin x all squared. Okay, so here we have something a bit like sine squared plus cos squared x. So let's do this. Let's write minus in brackets and then sine squared plus cos squared divided by 1 plus sine x squared. Because sine squared plus cos squared is equal to 1, we can write minus sine x minus 1 over 1 plus sine x all squared. And now let's factorise a minus 1 out, and then we get 1 plus sine x over 1 plus sine x squared. Now we can divide top and bottom by 1 plus sine x, and we're left with negative 1 over 1 plus sine x. So that's the answer to our derivative. Now sine x can vary between minus 1 and 1. Between those values all the way up to 1 we've got no problem, because when sine x is equal to 1 we have negative a half, which is fine. When it's 0 we have minus 1 divided by 1, which is fine. And all the way up to the point where we get to minus 1, the only issue is where we actually get to minus 1, where we get minus 1 divided by 0. So let's just verify. We are having x between minus pi by 2 and 3 pi by 2. So let's just very quickly think about our graph of sine x, which looks something like this. So when x is minus pi by 2 all the way up to 3 pi by 2, okay, so sine x is not equal to 0 between minus pi by 2 and 3 pi by 2, because crucially it's a strict inequality, so it doesn't include those two values. Okay, and sine x is only going to vary between 1 and minus 1, therefore the derivative is always going to be negative. Here we're asked to integrate the same expression as above, so let's go back and find it. We have cos x over 1 plus sine x. And we're integrating that between pi by 6 and pi by 2. This is one of the form where when we differentiate the bottom we get the top, because when we differentiate 1 plus sine x we get cos x. So this, very simply, when we integrate it, is 1 ln of 1 plus sine x between pi by 6 and pi by 2. So we get ln of 1 plus sine of pi by 2 minus ln of 1 plus sine of pi by 6 sine of pi by 2 is just 1. Sine of pi by 6 is a half. So we have ln 2 minus ln of 3 over 2. We're subtracting two logs so we can divide them. So we have ln of 2 divided by 3 over 2. We could times top and bottom of this fraction by 2 and end up with ln of 4 over 3. Here we've got a question on differential equations. So we're told that the gradient of this certain curve is proportional to y over x root x. So we'll start maybe by writing that dy by dx is proportional to y over x square root of x. We could write that as an equation. Dy by dx is equal to k times y over, and let's change this into index form. This is x to the power of 3 over 2. And now let's prepare to integrate by getting all of the x's on one side with dx and the y on the other side with the dy. So we end up with 1 over y dy is equal to k over x to the 3 over 2 dx. I think we're going to bring this up and express it in index form. So 1 over y dy is equal to the integral of k x to the negative 3 over 2 dx. Now let's integrate both sides. The left hand side we have ln y is equal to, and now let's increase the power of this by 1, that's negative a half. Divide by that new power, so dividing by negative a half is the same as multiplying by negative 2. So we get minus 2kx to the minus a half plus c. Okay, it wants us to express y in terms of x, so we'll take exponentials of both sides. So y equals e to the minus 2kx to the minus a half plus c. Just for clarity, I'm going to write this as e to the minus 2k over the square root of x plus c. And now we're going to substitute our two coordinates in. So we'll start with the coordinate 1, 1. So 1 is equal to e to the power of minus 2k over square root of x. Well, the square root of 1 is 1, so that's just minus 2k plus c. And our second coordinate is the coordinate 4, e. So e is equal to e to the power of minus 2k divided by the square root of 4. The square root of 4 is 2. So we get minus 2k divided by 2 plus c. So e is equal to e to the power of minus k plus c. We've got two equations and two unknowns. Let's start with this one and take logarithms of both sides here. When we do that, we get 1 is equal to minus k plus c. So we could write that k is equal to c minus 1 and substitute that into our other equation. So we have 1 is equal to e to the power of minus 2 times c minus 1 and plus c. So 1 is equal to e to the minus 2c plus 2 plus c. So e to the power of minus c plus 2 equals 1, and again we'll take logarithms of both sides. LN1 is equal to 0, so 0 is equal to minus c plus 2. So we get c is equal to 2. Substitute that back into number 1, k is equal to 2 take away 1, so k is equal to 1. So our equation is, where were we? Y is equal to e to the power of minus 2 times k, which is 1, so minus 2 over the square root of x, plus c, which is 2. 8b asks us to describe what happens to y as x tends to infinity. So I'm just going to recopy my answer from the previous one. We have y is equal to e to the power of minus 2 over the square root of x plus 2. Okay, so as x tends to infinity, square root of x is going to become a very, very large number. We have negative 2 divided by a very large number. So as x tends to infinity, y tends towards e to the power of, well, this is essentially 0 because this becomes a very small number, plus 2 because of this plus 2 here. So we end up with y tending towards e to the power of 2. Question 9 is a vectors question. It tells us the vertices of the triangle ABC have these position vectors. Let's first of all write these position vectors using column notation and maybe using lowercase letters. So instead of 2i plus 5k, that would be 2, 0, 5. B would be 3, 2, 3. And C is 1, 1, 1. The picture that we are trying to envisage looks something like this, okay, with A, B and C, and the vectors that we are given are describing the displacement of these points from the origin. So this is vector A, this is vector B, and this here is vector C. I'm just going to remove those because they're going to get a little bit in the way, but we need to imagine that those things are there. Okay, so to be able to show that angle ABC is a right angle, first of all let's draw in the angle ABC. ABC is this angle here. To find this angle here, to use the scalar product, first of all we need the two vectors pointing away from the point where the angle is, so pointing away from B. So that is the vector BA and the vector BC. Let's find the vector BA first of all. So the vector BA is equal to A minus B, because we are going to go backwards along the vector, the position vector to B, and forwards along the position vector to A. So A is positive, B is negative. So that is 2, 0, 5. Subtract 3, 2, 3. So we get minus 1, minus 2, 2. We're now going to do the same thing with BC. Our vector BC is C minus B. C minus B is 1, 1, 1. Subtract 3, 2, 3, which is negative 2, negative 1, negative 2. And we are now going to do the scalar or dot product between these two vectors. So BA dotted with BC, -1, -2, 2, dotted with -2, -1, -2, which is equal to -1 times -2 plus -2 times -1 plus 2 times -2. So 2 plus 2 minus 4, which equals 0. And when the scalar product is 0, that means the angle between them is 90 degrees. Therefore, angle BAC is 90. To show that triangle ABC is isosceles, let's first of all draw a quick sketch of our triangle from before. So this is B, this was A, and this was C. This is our right angle here. So the only way in which this could be isosceles is if these two sides are equal. Okay, because the right angle is here, there's no way that any two other sides could be equal. So what we're now going to do is we're going to find the length of these two vectors, the magnitude of the vectors. So let's find the magnitude of the vector BA from our previous part of the question. BA was -1, -2, 2. So to find the magnitude of that, that's -1 squared, -2 squared, plus 2 squared. I'm just going to double check those numbers. Yeah. So that is equal to the square root of 1 plus 4 plus 4. So the square root of 9, so 3. And then we're going to do the same thing for our vector BC. So let's just check. BC is -2, -1, -2. So -2 squared plus -1 squared plus -2 squared. So 4 plus 1 plus 4, which is the square root of 9, which is 3. Okay. Let's try and fit in a little sentence here. BA equals BC, therefore triangle is isosceles. Part C asks us to find the exact length of the perpendicular from O to the line through B and C. Let's draw a rough approximation of the situation. This could be the line BC, for instance. This could be our origin here. And the distance we're interested in finding would be this distance, which meets that line at a right angle. Okay. So first of all, we need an equation for the line going through B and C. That is not just the vector BC. We need the position vector of a point on the line and then a scalar multiple times by the directional vector going through BC. So we're going to use either the position vector of B or the position vector of C. We'll pick whichever one seems simplest. Let's just have a quick look at those again. So B was 3, 2, 3, C was 1, 1, 1. Looks to me like C might be the easier one to pick, although it doesn't matter. So we're going to choose 1, 1, 1, and then plus a scalar multiple, we usually use something like lambda for that, times by the vector BC, which again we've calculated up here. So BC was -2, -1, -2. Okay, that describes any point along this line here. Okay, so it would also describe whatever this position is here. I'm going to write it as a single column vector, this point, so 1 minus lambda and 1 minus 2 lambda. And now we want to do the dot product between this point here and the direction of the line, because what we've got here is this vector r. This is the red one that we've just found out here, going from the origin to any point on the line. And we want this to be at 90 degrees to the direction of the line. So we're now going to do the dot product between this and the direction vector of BC, -2, -1, -2. And we're going to set that equal to 0. So 1 minus 2 lambda, 1 minus lambda, and 1 minus 2 lambda, dotted with the direction vector of BC, -2, -1, -2, must be equal to 0 because we want the perpendicular. So it's at 90 degrees. So now we're going to multiply our components together. So 1 times -2 is -2 plus 4 lambda, that's the first one, minus 1 plus lambda, the second, minus 2 plus 4 lambda, and the third. And that must be equal to 0. Let's collect like terms here. So we have -5 plus 9 lambda equals 0. So 9 lambda is equal to 5. So lambda equals 5/9. It would be easy to think that you finished the question, but we haven't, because we actually want to find the length of this line. So we're now going to put this back into our equation for r. So r is equal to 111 plus 5/9 times -2, -1, -2. So we're going to end up with 1 minus 10/9. That's -2 times 5/9. 1 minus 5/9. And 1 minus 10/9. Okay, so here we're going to get -1/9, 4/9, and -1/9. So that is my vector from O to R, to the point on the line. We haven't yet found the distance though, which is what we were asked for. So we need to find the exact length of that, and we're going to do that using Pythagoras. So -1/9 squared plus 4/9 squared plus -1/9 squared, all of that square rooted. So 1/81 plus 16/81 plus 1/81. So add those up and we get 18/81, which is √2 times by the square root of 9/81. 9 divided by 81 is just 1/9, 1/9, and the square root of that is 1/3. So we get 1/3 times √2, or just √2/3. You can equally evaluate all of that using your calculator. Okay. Question 10 wants us to find this complex number in a Cartesian form. This basically means just to split up the real and imaginary components. Students often don't like these questions, but actually once you learn a few basic tricks, they're not too difficult. And for this one, the trick is to multiply by the complex conjugate of the denominator. So we're going to start with our 3i/a plus 2i and multiply top and bottom by the complex conjugate. So a minus 2i. Okay, and when we do that, we get 3ai on the top, and then we're going to get minus 3 times 2, which is 6i squared. Some of you will already realise that's minus 1. You could have simplified that already in the previous step. Okay, so now we're going to do a times by a, which is a squared. The two middle terms will cancel each other out, plus 2ai minus 2ai, so we're just left with our last terms, and we have 2 times negative 2, which is negative 4, and then times I squared again. Okay, so on the top we get 3ai. I squared is minus 1, so this is going to become plus 6. And on the bottom, a squared, and again I squared is minus 1, so this will become a squared plus 4. So now to separate these out into real and imaginary components, let's put our real component first. 6 over a squared plus 4 plus 3ai also over a squared plus 4. There we go, there's our real part, there's our imaginary part. The second part of this question is asking us about the argument of u star. This means the complex conjugate of u. So let's get our previous answer for u. So u is equal to 6 over a squared plus 4 plus 3ai over a squared plus 4. This means that the complex conjugate of that would be 6 over a squared plus 4, and instead of plus, it's minus 3ai over a squared plus 4. And we're now going to find the argument of this. The argument is the angle that this complex number makes with the real axis, or you might think of it as the x-axis, on an arctan diagram. So that would be arctan of the y component, or the imaginary component, divided by the x component, the real component. So we have negative 3a over a squared plus 4 divided by 6 over a squared plus 4. And we know that that should be pi by 3. So now we are going to simplify what's in the brackets here. We can times top and bottom by a squared plus 4 and just be left with inverse tan of minus 3a over 6 is equal to pi by 3. And then we can simplify further and just get minus a over 2 is equal to pi by 3. And then we are going to take tan of both sides, and we get minus a over 2 is equal to tan pi by 3. Tan of pi by 3 is square root of 3. Multiply both sides by 2 and we get minus a is equal to 2 root 3, so a is equal to minus 2 root 3. Part B is asking us to shade regions on an arctan diagram. There are not too many different types of loci to learn. This one is a perpendicular bisector. This one is a circle. We'll start by just drawing our axes for our arctan diagram. So there's our imaginary axis. Here's our real axis. Okay, so this represents the perpendicular bisector between the point 2i, so that's 2 on our imaginary axis, and 1 plus I, or a bit like the point 1, 1. So 1 on our real axis and 1 on our imaginary axis. So we want the perpendicular bisector of these 2 points, which is going to go through this point I and this point minus 1. Let's try and get this as close to a 45-degree angle as possible. There we go. So that's our first part, and we want the points that are closer to 2i than to 1 plus I. So we would be looking at this side of the line here, the top left side. Before we do that, we're going to consider the second part. And the second part is a circle centred at the point 2 plus I. So 2 plus I is here. And the circle has a radius of 2. Now this is 2 away from that y-axis, the imaginary axis, so it should be a tangent here. It should go down below, about 1 below the real axis there, and about the same distance there, and somewhere up here. So it's going to look something like, and I'm sure you'll be able to do a better sketch than me, something like that. And the region we want is within the circle, so that would be the part that is within the circle and on the top left of that line. So that's the region we want there. Our final question asks us to find the least value of the argument of z for points within that region. So z represents any number coming from the origin here to any point in that region. So the complex number z with the smallest argument is the one with the lowest angle, the smallest angle it makes with the real axis. So that would be the point on the very extremity of that region there. So this is the line we're looking for. Any point past that, any point elsewhere in the region would have a greater angle. So this is the one we're looking for. So really this is the key point we need to identify. Now from sight it looks like it's directly above where the centre is. I'm just going to verify that that's also on that straight line. So if we think about where the top of the circle is to begin with, that would be where the real component is 2 and the imaginary component is 3. So that looks like the point 2 plus 3i. Can we verify that that is also on that straight line? Well, we are starting at the point 0, 1, and this has a gradient of 1. It's at 45 degrees, so we're going across 1, up 1, so this would be the point 1, 2, across 1, up 1, so this would be the point 2, 3, or 2 plus 3i. So 2 plus 3i is the point of intersection of both of these things. There are slightly more thorough ways to do this, but for 2 marks, I don't think we're required to. So we'll just stick with that slightly easier way. And all we want to find now is the argument of this number. So the argument of 2 plus 3i. Okay, and the argument of 2 plus 3i is arctan of the imaginary component divided by the real component. And when we work that out, we find it to be, and well, in radians, 0.983 radians. I hope you enjoyed the video. Best of luck with your revision and with all of your exams, and see you in the next video.